NASA is preparing one of its strangest telescope missions ever. It will not launch on a rocket. Instead, NASA plans to lift a giant telescope above Antarctica under a helium balloon larger than a football field, send it to the edge of Earth's atmosphere, and use it to observe a hidden part of the universe that ground telescopes cannot see. The mission is called ASTHROS, the Astrophysics Stratospheric Telescope for High Spectral Resolution Observations at sub-millimeter wavelengths. This NASA balloon telescope is designed to study far infrared light, star formation, the Milky Way, nearby galaxies, and the invisible physics behind how stars and planets are created. And the reason NASA needs ASTHROS is simple. Some of the most important evidence in the universe never reaches the ground. Earth's atmosphere blocks it. So instead of sending this telescope all the way into deep space, NASA is trying something different. It is lifting ASTHROS above the part of Earth that gets in the way. If this mission works, it could help answer one of the biggest questions in astronomy. How does the universe turn cold clouds of gas and dust into stars, planets, and eventually worlds like Earth? To understand why ASTHROS matters, we have to start with the problem every telescope on Earth faces. The atmosphere protects life, but it also hides parts of the universe. Visible light can reach the ground. Some radio waves can reach the ground, but far infrared light is heavily absorbed by Earth's atmosphere, especially by water vapor. That creates a blind spot in astronomy. The coldest and most important parts of the universe often do not shine brightly in visible light. Star-forming clouds, hidden gas, young planetary systems, and dusty regions inside galaxies reveal themselves in wavelengths human eyes cannot see. Some of that light carries information about the raw material of stars. Some of it comes from the gas that galaxies use to keep creating new suns. Some of it comes from the early environments where future planets are still being assembled. The evidence is out there, traveling across space for thousands, millions, or even billions of years. But when it reaches Earth, our atmosphere blocks much of it before surface telescopes can study it. That is the gap ASTHROS is built to cross. NASA does not need this mission to become another James Webb Space Telescope. Webb is already one of the most powerful observatories ever created. ASTHROS has a different job. It is designed to rise high enough above the atmosphere to observe far infrared light from a place ground telescopes cannot reach. That is why NASA is building a telescope that flies under a balloon. The scale of the mission is difficult to picture. When the helium balloon is fully inflated, it will be roughly the size of a football stadium. Beneath it will hang a full scientific observatory with a telescope, a science instrument, solar panels, electronics, communication systems, and a gondola designed to survive a high-altitude flight above Antarctica. At the center of the observatory is a lightweight 2.5-meter telescope, making ASTHROS one of the largest telescopes ever designed to fly beneath a high-altitude balloon. The mission is planned to launch from Antarctica because the continent gives NASA a rare advantage. During the Antarctic summer, stratospheric winds can carry long-duration balloon missions around the continent. The sun remains above the horizon for long periods, which helps power the solar panels. The remote environment also gives NASA space to launch and recover large scientific balloon payloads. ASTHROS will rise to around 130,000 feet, or about 40 kilometers above Earth. That is far above commercial aircraft. It is still below orbit, but it is high enough to escape most of the atmospheric interference that blocks far infrared astronomy from the surface. From there, ASTHROS can operate like an observatory at the edge of space. It will not be permanent. It will not be as famous as Hubble or Webb, but it is aimed at a part of the universe that remains difficult to study even after decades of modern astronomy. NASA is not sending ASTHROS far away. NASA is lifting it just high enough to reveal what Earth normally hides. The real target of ASTHROS is not only a nebula, a galaxy, or a young star system. The real target is star formation. At first, the birth of a star sounds simple. A cloud of gas and dust collapses under gravity. The center becomes dense and hot. Eventually, a star ignites. But the universe is much more complicated than that. Galaxies are filled with gas, yet they do not turn all of that gas into stars at once. If gravity were the only force involved, galaxies like the Milky Way should have burned through far more of their star-forming material long ago. Something controls the process. Something decides when gas collapses, when it stops collapsing, and when a cloud is destroyed before it can form more stars. That process is called stellar feedback. Stellar feedback is what happens when stars begin changing the environment around them. Massive young stars release intense radiation. They drive powerful stellar winds. Later, some of them explode as supernovae, sending enormous amounts of energy back into the gas and dust around them. These stars are born inside clouds, and then they begin reshaping the same clouds that created them. This is the paradox ASTHROS is trying to understand. Stars are both creators and destroyers. They are born from gas, but once they ignite, they can blow that gas apart. They can stop new stars from forming, but they can also compress nearby material and help trigger the birth of more stars. So the question becomes much deeper than simply asking where stars are born. The real question is how the universe controls star birth without letting galaxies burn through all their fuel at once. ASTHROS is designed to look directly at that hidden struggle. We already have breathtaking images of star-forming regions. Hubble has shown towers of gas and dust. James Webb has revealed newborn stars hidden inside infrared clouds. Some of the most famous images in astronomy show nebulae glowing with color, structure, and detail. But a beautiful image is not the same as understanding the physics. An image can show where the cloud is. It can show where the light is. It can show the shape of the region. But ASTHROS is being built to answer a different question. What is the gas actually doing? Is it collapsing inward, being pushed outward, heating, cooling, breaking apart, or being compressed into the next generation of stars? To answer that, astronomers need more than a picture. They need motion, density, chemical fingerprints, and a way to measure how energy moves through star-forming regions. ASTHROS will use high-spectral resolution observations to study far infrared light from ionized gas. One of the mission's key goals is to map specific forms of ionized nitrogen. These signals can help trace the places where massive stars and supernovae are injecting energy into surrounding gas. In simpler terms, ASTHROS is looking for the fingerprints left behind by massive stars. It is trying to map the invisible aftermath of stellar violence. A nebula is not just a glowing cloud. It is a moving system where gas is being pushed, carved, compressed, scattered, and recycled. Some of that material will be lost. Some of it may become the next generation of stars. Some of it may eventually become planets. ASTHROS is designed to turn that hidden motion into a map. One of the main places ASTHROS will study is our own galaxy, the Milky Way. The Milky Way is not only the galaxy we live in, it is also the closest laboratory for understanding star formation in detail. Inside our galaxy are enormous clouds where stars are still being born. One of the planned targets for ASTHROS is the Carina Nebula, one of the most dramatic star-forming regions in the Milky Way. Carina is already famous because Hubble and James Webb have shown its cliffs, pillars, dust clouds, and newborn stars in incredible detail. But ASTHROS is not going there to repeat those images. It is going there to measure what those images cannot fully reveal. The telescope will study far infrared light from gas affected by massive stars. It will help scientists understand how energy moves through the region, how gas responds, and whether massive stars are stopping star formation or triggering more of it nearby. That is why the Carina Nebula is so valuable. It gives NASA a close-up view of the same process that shapes entire galaxies. If scientists can understand stellar feedback inside the Milky Way, They can use that knowledge to understand star formation across the universe. The Milky Way becomes the close-up. Other galaxies become the larger story. The universe is violent, but it is not wasteful. When massive stars blast radiation into space, it may look destructive. When supernovae explode, they may seem like endings. When clouds are torn apart, it may look like star formation is being shut down. But that same destruction can also become part of the next beginning. Energy from massive stars can carve cavities in clouds, but it can also push material into denser regions. Supernovae can scatter heavy elements into space, but those elements can later become part of new stars, planets, moons, and atmospheres. The material is not simply lost, it is recycled. This is one of the most powerful ideas in astronomy. The universe builds by breaking things apart and using the remains again. Stars are born from gas. Stars reshape that gas. Some stars die and return enriched material to space. That material becomes part of new clouds. New clouds become new stars. Some of those stars form planetary systems. ASTHROS is aimed at one of the hidden stages in that chain. It is not only measuring gas. It is studying how the universe keeps the cycle going. A balloon telescope may sound simpler than a space telescope, but simple does not mean easy. ASTHROS has to work where every system matters. The telescope must point accurately beneath a giant balloon. Its detectors must stay extremely cold. Solar panels must keep it powered. Communications must send data back to Earth. And the flight has to survive the Antarctic stratosphere. At about 130,000 feet, ASTHROS will operate above most of the atmosphere, but there is no repair crew at that altitude. If the pointing is unstable, the data suffers. If the cooling fails, the instrument's own heat can overwhelm the faint, far-infrared signals. If the weather is wrong, the launch waits. That is why ASTHROS feels less like a normal telescope and more like a scientific expedition. NASA has to send a precision observatory to Antarctica, lift it into the stratosphere beneath a massive balloon, and collect real astrophysics data while drifting high above the ice. The goal is not just to fly. The goal is serious science from one of NASA's strangest observing platforms. One of the most important parts of ASTHROS is the cooling system. Far-infrared detectors are extremely sensitive to heat. If the instrument is too warm, its own thermal signal can interfere with the faint light coming from space. That means ASTHROS has to keep its detectors incredibly cold. NASA has said the detectors need to be cooled to about 4 Kelvin, only a few degrees above absolute zero. Many missions use liquid helium for cooling, but liquid helium is limited. Once it runs out, the cooling stops, and the mission can be limited by that supply. ASTHROS is designed to use an electric cryocooler powered by its solar panels. That engineering choice captures the mission perfectly. A telescope hanging beneath a stadium-sized balloon over Antarctica will use sunlight to help power a system that cools its detectors close to absolute zero. All so it can detect far-infrared light from star-forming regions across the galaxy. It is an unusual combination: a balloon above the ice, solar panels in Antarctic sunlight, a telescope pointed into the Milky Way, and detectors cold enough to capture light that Earth's lower atmosphere normally blocks. This is why ASTHROS is not just a clever idea. It is a serious observatory built around one difficult scientific window. And ASTHROS is not only about one balloon flight, it is also about what comes after. NASA balloon missions can test new technologies in conditions much closer to space than any normal laboratory can provide. A full space telescope is expensive, slow, and difficult to repair once it launches. A balloon mission can test instruments, detectors, cooling systems, pointing systems, and observing strategies at lower cost. In some cases, The hardware can even be recovered after the flight. That makes ASTHROS a pathfinder. It can help prove technology that may support future far-infrared observatories. It can help scientists refine the questions larger missions should answer. It can show what works before those ideas are placed on a more expensive spacecraft. This matters because the future of astronomy will not only depend on building bigger mirrors. It will depend on seeing the universe in wavelengths we still struggle to reach. Cold gas between stars, dust around young suns, galaxies forming new stars, and planetary systems still under construction are all part of the hidden universe that far-infrared astronomy can reveal. ASTHROS is part of that path. It is a focused NASA mission designed to open a narrow but powerful window into the hidden side of starbirth. The deeper story behind ASTHROS is that the universe has been giving us incomplete information. When we see a nebula, we see the surface of a process. We see color, shape, and light. But behind that image is motion. Gas is flowing. Radiation is pushing. Winds are carving. Gravity is pulling. Supernovae are injecting energy. Some clouds are being destroyed, while others are being prepared for the next generation of stars. That is the process ASTHROS is trying to measure. It is not chasing beauty. It is chasing the mechanism behind the beauty. Every star in the night sky began inside a cloud. Every planet began as material around a young star. Every galaxy carries the history of how gas became stars, how stars returned energy to space, and how that material was used again. ASTHROS is aimed at one of the hidden links in that chain. The link between cold gas and new stars. The link between massive stars and the clouds they reshape. The link between star formation and the long evolution of galaxies. And somewhere far down that chain is the story of planets like Earth.
NASA's ASTHROS mission is easy to underestimate because it does not look like the future of astronomy at first. It is not a giant observatory unfolding in deep space. It is not a spacecraft traveling to another planet. It is a telescope under a balloon, rising above Antarctica into the stratosphere. But that is exactly why it matters. ASTHROS is built around a simple but powerful idea. If Earth's atmosphere blocks the evidence, then lift the telescope above the part of Earth that gets in the way. From there, this NASA balloon telescope can observe far-infrared light from star-forming regions, the Milky Way, nearby galaxies, and young planetary systems. It can help reveal how massive stars shape the clouds around them, why galaxies keep forming stars instead of burning through their gas all at once, and how the birth of stars connects to the birth of planets. Because the universe does not create only through calm and order. It creates through pressure, radiation, collapse, destruction, and renewal. Stars are born. Stars fight back against the clouds that form them. Some material is scattered, some returns. Some becomes new stars. And around some of those stars, planets begin to form. ASTHROS is designed to watch that hidden cycle in a way ground telescopes cannot. A telescope under a stadium-sized balloon. A launch from Antarctica. A flight near the edge of the atmosphere. A far infrared view of star formation that Earth normally blocks. This is not the most famous NASA mission, but it may help explain the process behind almost everything we see when we look up at the night sky. Because before there are planets, before there are oceans, before there are worlds, and before there is anyone to look back at the universe, there must first be stars. And ASTHROS is being built to understand how the universe makes them.